All right, how's it going, guys? Today in this video, we're going to finish up 6.2, or really just all module 2, or module 6, sorry, we're going to finish it all up. So this is the warm-up for the day. So go ahead and pause the video, see if you can figure it out on your own. All right, so hopefully you paused it, hopefully you did the problem. So this problem right here, what I can see is that I have a negative slope. Well, I have a, my end behaviors is I'm going from the bottom left to the top right. So if I start from the bottom left and I go to the top right, I'm gonna have a function that looks something like this, like a y equals x function, right? Start from the bottom left and the top right. So if I have a function similar to this right here, erase that real quick, a y equals x. So that tells me I'm gonna be I have to be an odd degree function with a positive leading coefficient. I start from the bottom left, I go to the top right. That's very similar to y to the x, which is an odd degree polynomial with a positive leading coefficient. So that means right away I can cross out a and b because those both have negative leading coefficients. So it's either c or d, and they all have the same x-intercepts of -2, 1, and 2 and 3. Sorry, both those c and d's have all the same x-intercepts to the right. What I need to do now is I need to figure out, well, is the leading coefficient 2 or 4? And I can figure that out by plugging this point into both those points and seeing which one works. So I'm going to plug in my x value of 2 into c and d and see which one gives me -16. In this case, I think d is the one that ends up working because we get f of x will equal 4 times 2 minus 1, 2 minus 3, and 2 plus 2. If you plug it into d, which is 4 times, that's 1, that's -1, and that's 4. So this becomes just -1. 4 times -1 is -4, times 4 is -16. So for the warm-up, you should have got this. All right, so let's go ahead and finish up the notes now. On example 10, I'm told that p of x will equal 3x to the 7th minus 15x to the 5th plus 12x cubed. So the problem with this example compared to example 8 and 9 that we did yesterday is that example 10 is not in factor form. So I need to factor this out. So I'm going to go to the bottom right here. I'm going to factor that out. So I have, let's do it over here, p of x equals 3x to the 7 minus 15x to the 5th plus 12x cubed. So I'm going to factor this out. And when it comes to factoring out polynomials, the very first thing you always want to do is look for a GCF. And with all of these, I see that I have a GCF of 3x cubed. And when I factor that out, I'm left with x to the 4th minus 5x squared plus 4. But I'm not done yet. I still need to factor this part out right here. And x to the 4th minus 5x squared plus 4, that actually ends up factoring out to x squared minus 4 times x squared minus 1, and we'll bring down that GCF that we pulled out. So if it's a little hard to see why factored out to x squared minus 4, x squared, and x squared minus 1, let's actually take that part to the side over here so I can kind of explain what's happening. I have x to the 4th minus 5x squared plus 4. And we're not really used to factoring trinomials that aren't quadratics, right? We're used to saying something like x squared minus 5x plus 4, not x to the 4th minus 5x squared plus 4. But you could play around with these numbers a bit, and I can say, well, let's say a equals x squared. Let's just say I'm setting a equals x squared. You can do that. And I'll plug in my a into my formula right above it, and what I get is a squared minus 5a plus 4. And that's something that I know how to factor out. I can factor that out. And that's going to factor out to a minus 4 times a minus 1. Because what I want is factors of positive 4 that add up to give you 5, or -5, sorry. So -4, -1, multiply to positive 4. -4 and -1 add to -5. And I want this to be put back in terms of x, where I'm not dealing with a's when I'm graphing this function. I want it in terms of x. So I'm just going to plug in this a equals x squared back in to get x squared minus 4, x squared minus 1. That's kind of what's happening when we factor out that x to the 4th minus 5x squared plus 4. So this is kind of just an aside to see what's happening. If you're able to factor that out without doing all this nonsense right here, ignore it. That's kind of just what's happening. But we're not done here because x squared minus 4 and x squared minus 1, they both still factor down. They're both difference of squares. So we get x minus 1, x plus 1 from x squared minus 4, and we get x, sorry, not minus 1, should be plus 1, or plus 2, sorry. So we're going to change these. It should be x minus 2, x plus 2, and x squared minus 1. That's what gives us x minus 1, x plus 1. All right, so that's my factored form, and this is also going to give me my x-intercepts. So what I'm going to do now is I'm going to go ahead and graph my x-intercepts, because if you remember from yesterday, the very first steps are always graph your x-intercepts and also graph your y-intercepts. That should always be your first step. So from here, I see that this x cubed right here gives me an x-intercept of 0. And that also actually ends up being your y-intercept too, right? Your origin or your 0, 0 point is your x and your y-intercept. So we already have our y-intercept as well. X minus 2 and x plus 2 gives you 2 and negative 2 respectively. So I have negative 2 and 2. And then x minus 1 and x plus 1 gives you 1 and negative 1 respectively as well. So we have 1 here and negative 1 here and 0 right there. So those are all my x-intercepts. And my x-intercept and my y-intercept actually. So what I'm going to do now is I need to figure out how to graph it, and then I'm going to fill out all these stuff right here on the side. So first is I'm going to figure out what my leading coefficient is going to be. So if I look at this p of x right here, let me go ahead and label it actually. This p of x right here, my leading coefficient is 3. But that's the same exact leading coefficient as the one in the original p of x. And that's because they're the exact same equation. One just factored out and the other one isn't. So they have the same exact leading coefficient of 3. And that means they also should have the same exact degree of 7. And if we go back to this p of x right here, I can see that I also have 7, right? I have a 3, that's 4, 5, 6, and 7. It's the same exact polynomial. One just factored out, the other one isn't. Either way, you're going to have the same degree and same leading coefficient of 3 and 7. Well, leading coefficient of 3 and a degree of 7. So that's what I have. So I see that I have an odd degree polynomial with a positive leading coefficient. So that means I'm going to be very similar to y equals x, which is an odd degree polynomial, right? X to the first power, 1 is odd. That's positive. So I'm going to have the same end behaviors as y equals x. Or in other words, I start from the bottom left and I end to the top right. So now I'm going to go through all these x-intercepts. I'm going to see, well, what kind of, how am I crossing those x-intercepts? So if I go back to my factored form right here, I can see that, well, every single factor here, each individual factor of this polynomial has a degree of 1 except for this x cubed. So I'm going to go straight through each x-intercept except at x equals 0. At x equals 0, I'm going to go through it kind of cubically, or in other words, I'm going to have a concavity change through the 0 x-intercept, or I'm going to kind of curve into it, then curve back out. And that's what I'm going to do. I start from the bottom left because I have an odd degree polynomial with a positive leading coefficient. And I'm going to go through each of these x-intercepts, just go straight through them, except for at 0, 0, where I kind of curve into it and curve back out. So I start from the bottom. I'll go straight through that, straight through that. I'm going to kind of curve into that one, straight through this one, and finally straight through that last one to get a graph that looks something like that. It's kind of ugly, but it should look roughly like that. And then from here, I need to know how many local maximums, local minimums, global maximums, and global minimums that I have. Number of local maximums, I have 2. Local minimums, I also have 2. So my local maximums are right here and here. Let me actually go ahead and write that in red as well. That's 2. And then for the local minimums, that's going to be the ones right here and right here. So I have 2 local minimums. And then I have 0 global maximums and 0 global minimums because this graph goes up forever and it goes down forever. Or in other words, any maximum number you give me, I can always give you another number bigger than it that's also on the graph. And same thing with the minimums. Any minimum value you try to give me, I can always give you another minimum value that's smaller than that value that you gave me. Because it's going up to infinity and going down to negative infinity. There are no global maximums or minimums. So this is what it's going to look like. Here's the full work. I'll spread out, take a picture, or copy it down if you need to. But here's all the work. All right, let's keep going. Now, example 11, I'm told that if f of negative 7 equals f of 4, which equals f of 2, which equals f of 1, and that all equals 0, and f of 3 equals 10, and I'm told f of x is a polynomial of degree 4, find f of 0. So let's kind of break this up part by part. In this first part right here that I'm underlining in purple, that's just telling me when x is negative 7, x is 4, x is 2, and x is 1, my y values all equal the same thing, which is 0. Or that's really just kind of a complicated way to say that your x-intercepts are negative 7, 4, 2, and 1. And then I'm told that f of 3 equals 10. That tells me I have a point 3, 10. And I'm also told that f of x is a polynomial of degree 4. We need to find f of 0. So when I'm told I have a polynomial of degree 4, that's telling me how many x-intercepts I'm going to have, right? So in this case, I have 4 x-intercepts, negative 7, 4, 2, and 1. So if I have 4 x-intercepts and I have a degree of 4, that tells me that each of these x-intercepts are going to happen only once, right? The total amount of x-intercepts have to equal your total degree, and that could mean that some of your x-intercepts happen more than once, right? And we've seen examples of that before, like this example we just did right here. This x-intercept of 0, that happened 3 times. So the total amount of x-intercepts have to equal the degree of the polynomial. So I'm going to go ahead and graph this out, or not graph it out, sorry. I'm going to write it out. So f of x will equal some leading coefficient of a that we don't know yet. And I'm going to plug in all these x-intercepts. So x minus negative 7 is x plus 7. Then I have x minus 4. Then x minus 2. Then finally x minus 1. Those are all my x-intercepts. And they all happen once because if I add up the degrees of this factored form right here, I get 4, and that's what I want, a polynomial of degree 4. And now I can use this point that I'm given, the 310. I can plug that in to solve for a. So I need to know what my leading coefficient actually is so I can solve for f of 0. So when y is 10, I get 10 equals a times my x value of 3 plus 7, then 3 minus 4, 3 minus 2, then 3 minus 1. So 10 equals a times 10. 3 minus 4 is negative 1. 3 minus 2 is positive 1. And 3 minus 1 is 2. So I can divide this whole part, the right side, by 10 on both sides because these 10s cancel out. And we get 1 equals a. Negative 1 times 1 is negative 1 times 2 is negative 2. Or a equals negative 1/2. So that's my a value. So I can plug it back into my f of x formula. So f of x equals negative 1/2. What was it? X plus 7 times x minus 4, x minus 2, then finally x minus 1. So that's what my f of x function is going to be. But I also want to solve this for when I need to solve this when x equals 0. So I need to figure out f of 0 is going to be. And f of 0, that happens when x is 0. So we're going to plug in 0 for x. So I get 0 plus 7, which is just 7. 0 minus 4 is negative 4. 0 minus 2 is negative 2. Then 0 minus 1 is negative 1. I plugged in x equals 0 into this function because I want f of 0. So I'm going to solve this all out. So negative 2 and negative 1, that gives me a positive 2. That gives me a negative 8. Then I have negative 8 times negative 1/2. That gives me a positive 4 times 7. So I multiply this negative 8 with this negative 1/2 to give me a positive 4. 4 times 7 is 28. So f of 0 equals 28. All right, and let me go ahead and put this in the full screen as well, in case you need to take a picture or whatever you need to do to copy it all down to see exactly what's happening. All right, let's keep on going. Now we're on example 12. On example 12, we're told to write the equation of a polynomial of degree 5 with intercepts solely at negative 4, 0, negative 2, 0, 0, 4, and 1, 0, where f of negative 3 equals 4, and where the absolute value of the leading coefficient is 1/4. So there's a lot going on here. So let's kind of just break this down part by part to see what's happening. So the first thing I'm told is that I want to write the equation of a polynomial with a degree of 5. So a degree of 5 means I have to have 5 x-intercepts, even if some x-intercepts happen more than once. And my only intercepts that I have are these right here. And I'm also told f of negative 3 equals 4, or in other words, at the point negative 3, 4. And I'm told the absolute value of the leading coefficient is 1/4, or in other words, let's write this over here. The absolute value of A equals 1/4. Or in other words, your leading coefficient could be 1/4 or negative 1/4. We don't know. We're going to use all this information that we have to kind of figure it out. All right, so let's go ahead and see what happens when your A is positive 1/4. Let's try that first. So I have a positive and a negative. Let's see what happens when our A value is positive. So I want to see, well, does it work when A is positive 1/4? So what I'm going to do for that is I need to figure out, well, a general equation. I need to know, well, which x-intercept happen more than once. So to do that, what I'm going to do is I'm going to draw a graph, and I'm going to label out all the intercepts that they give me. So my intercept that they give me is negative 4, 0. So I'll put this over here. Negative 2. I have 0, 4, my y-intercept, and 1, 0. And I'm told that I have a odd degree polynomial. So if I have an odd degree polynomial, that means I start either on the top and I end the opposite way. So if I start on the bottom left, I go to the top right. If I start top left, I go to the bottom right. Right? You're just kind of going you're ending the opposite way you start. But here I'm told, I'm trying to see, well, what happens if my leading coefficient is positive? I want to know, well, if I have an odd degree polynomial and my leading coefficient, my A value is positive, what's going to happen? But if I have a positive leading coefficient, that means I'm going to start from the bottom left and I'm going to end in the top right. So I need to figure out, well, how can I draw this graph, this degree of 5 polynomial, so that I start from the bottom left and I go to the top right while hitting each one of these x-intercepts, or x-intercepts and y-intercepts. So this one takes a little critical thinking to figure out because it can be a little tricky to figure out. But what you end up getting is that the only way to draw this is if you start from the bottom left, we go through negative 4 once, we bounce off negative 2, we hit that 4, we bounce off 1, and we go back up. This is the only way to make a 5th degree polynomial graph with a positive leading coefficient with these intercepts. It's pretty much the only way to do it. So what that tells me when I want to graph this function is that my f of x will equal my leading coefficient of 1/4, and then I have all these x-intercepts. So when my x-intercept is negative 4, I went straight through that point. So that means I have a degree of 1. So I have x plus 4 to the first power. If you go straight through a point, that means you have a degree of 1. That's what's happening here. For x equals negative 2, I kind of touched that point and I bounced off of it. So when I bounce off of it, that means you have a degree of 2. So x plus 2 squared, right? X minus negative 2 is x plus 2 all squared. And then for positive 1, I bounce off that one as well. So it's x minus 1 all squared. And I can see here this is a 5th degree polynomial. I have 2 here, a 2 here, and a 1 right here. That adds up to 5. And that's what I graphed. So I have a 5th degree polynomial with a positive leading coefficient. So now I need to see, well, does the point negative 3, 4, does it exist on this equation? So I'm going to plug in my x and y on this graph to figure out. So I get 4 equals 1/4 times negative 3 plus 4 to the first power, negative 3 plus 2 squared, and negative 3 minus 1 all squared. So we'll simplify this out. 4 equals 1/4. Negative 3 plus 4 is 1. Negative 3 plus 2 is negative 1. Squared is also positive 1. Negative 3 minus 1 is negative 4. All squared. Did I get it wrong? Negative 3, positive 4. Okay, yeah, that's right. Negative 3 minus 1 is negative 4. And negative 4 squared, that, don't know why I did that, but negative 3 minus 1 is negative 4. And negative 4 squared is a positive 16. So what I get is 4 equals 1/4 times 1 times 1 times 16. These kind of go away, so it's really just 1/4 times 16, or 16 divided by 4, which is 4. So 4 equals 4, and that's right. So that means this is the real the real leading coefficient. My leading coefficient is a equals 1/4. So this is right here this right here is my degree, or my equation of the polynomial. But just because we figured it out, we're going to go ahead and do the other a value as well, just to kind of see what happens if we didn't solve for the right one first. So we're going to solve for the other one as well. So let's see what happens if I solve for the negative leading coefficient first. So same thing. I'm going to draw a graph to kind of just see what's happening with this function. So my x-intercepts are -4, -2, and 1. So I have -4, -2, and 1, and a y-intercept of 0, 4. So in this case, I have an odd degree polynomial because my degree is 5 with a negative leading coefficient. So in this case, I start from the top left and I end going to the bottom right. An odd degree polynomial means you go different ways. Negative means you start from the top left and go to the bottom right. So in this case, I have to start from the top left and going to the bottom right. And I need to figure out a way to draw this graph in a way where I hit all these x-intercepts and y-intercepts and go the opposite way. So again, this is going to take some kind of critical thinking to figure out because it can be a little tricky. But if you do it correctly, what you end up getting is that it should look something like this. We're tangent at -4, -2. We bounce off that and go straight through 1. That's what you're going to end up getting. It should look something similar to that. So if I was to graph my function, or not graph my function, sorry, if I was to write my function from this graph, I get f of x equals this leading coefficient of -1/4 multiplied by each of these x-intercepts. So x minus -4 is x plus 4. And I'm tangent at that point, right? I touched it and I bounced back off. So that means I'm going to be squared there. And same thing with x minus -2 or x plus 2. I also bounce off that point. I'm tangent to it. I touched it and bounced back off. That means I'm going to be squared there as well. And then at the x-intercept of 1, I have x minus 1. And I went straight through that point. So I have a degree of 1 there. And I see that I have a degree of 5 of this function here. That's exactly what I wanted. I wanted a degree of 5 with a leading coefficient of -1/4. That's what the graph shows, and that's what I have here. So what I'm going to do now is I need to make sure that the point -3, +4 actually exists in this graph. So I'm going to plug it in, and I get that 4 equals -1/4 times -3 plus 4 all squared times -3 plus 2 squared times -3 minus 1. So I get 4 equals -1/4. -3 plus 4 is 1. 1 squared is just 1. -3 plus 2 is -1. -1 squared is also +1. -3 minus 1 is -4. And it's just raised to the first power, so nothing happens there. So what I get is -1/4 times 1 times 1. These just go away. So I really just have -1/4 times -4, which is just a +1. 4 doesn't equal 1. That doesn't make any sense at all. So that's going to be wrong. So my answer was what I originally had right here in red. And that's what it's going to look like, or what happens if you don't have the right leading coefficient. You get some nonsense like 4 equals 1 that doesn't make any sense. So here's all the work to kind of see what's happening. All right, just go on to the last problem. And on this one here, I'm told what n behaviors are possible for the graph p of x equals -2x times x plus 3 all raised to n plus 1 times -x plus 2 raised to 2n for any positive integer n. So first thing I'm going to do is this p of x kind of bugs me. I don't like this negative right there. So first thing I'm going to do is I'm just going to rewrite this. P of x equals -2x times x plus 3 raised to the n plus 1. And when I factor out that negative, I get -x minus 2 raised to the 2. So that negative kind of bugged me. I don't like having it on the x itself. I'm going to factor out and have it like that. All right, so that's what my p of x is. I want to see, well, what possible n behaviors can I have? So if I look at this graph right here, or not the graph, the function right here, I have my leading coefficient of -2. That's not going to change. My leading coefficient is going to be -2. That's going to be that. But what will change is if my degree of the function is either odd or even. So that's what I'm going to do. I'm going to figure out what n values can I put in to change this function to an odd degree polynomial to an even one. And I'm going to look at both those cases to see, well, what's kind of happening with these n's. That's what changes with n, right? N can change if it's an odd degree polynomial or an even degree polynomial. So I'm gonna look at both those cases and ultimately decide, well, what n behaviors are actually possible for this graph. So let's keep this in red. Let's try n equals 1. When n equals 1, what I get is p of x equals negative 2x times x plus 3 all squared, because 1 plus 1 is 2, times negative of x minus 2. I'm not sure I put 1 there, but it should be 2. All raised to the second power, because it's just 2 times 1 or just 2. So in this case, I have an odd degree polynomial. So this gives me an odd function. So what I want to do first is I want to get rid of this negative right here. So what I can get rid of that negative is, well, I can just square, right? It's its own term there, and just like a quadratic before, it's kind of like your b value you had before. You can just square that b value and put it with your a's. So negative 1 squared just gives you a positive 1. So really, let's keep it with red. Really, that negative just kind of goes away. It is absolutely right. I can square that negative. It goes away because negative 1 squared is just 1. And 1 times negative 2x is just going to be negative 2x. So this is what I have. So this graph, I have a negative leading coefficient, right? It's negative 2, and a degree of 5, because I have a 2 here, a 2 here, and this x is raised to the first power. So I have a degree of 5 of an odd degree polynomial with negative leading coefficients. So, I mean, if you want to graph this, we could graph this really quickly. It's not really that hard. So I have x-intercepts at negative 3, at 0, and positive 2. So because it's an odd degree polynomial with a negative leading coefficient, I start up and I go down. At 3, I bounce off of it. At negative 3, sorry, I bounce off of it. And at 2, I bounce off of it. At 0, I go straight through it. So it's going to be something like that. So my n behavior here, when coefficient, when the n makes the polynomial an odd degree polynomial, is as x goes to infinity, f of x goes to negative infinity, and as x goes to negative infinity, f of x goes to positive infinity. So that's when n equals 1, or when we get an odd degree polynomial. Well, now let's figure out what happens if I put an n value in that makes it a even degree polynomial. So 1 made it odd, so maybe 2 will make it even. Let's figure out. So we'll plug in p of x. We put in 2 for n. What we end up getting, negative 2x, x plus 3, raised to the 2 plus 1, which is 3, times, what is it, negative x minus 2, all raised to the 2 to the n, 2 times n, or in this case, 4. So first thing I'm going to do here is also get rid of this negative right here. And just like before, I can just raise it to the 4th power and take it outside. So negative 1 to the 4th power is just a positive 1. So just like last time, it just goes away. So p of x equals negative 2x, x plus 3 cubed, times x minus 2 to the 4th power. Right? Anytime you have two things being multiplied together and it's all raised to a certain power, you can kind of distribute that that power in. So distribute this 4th power to the negative and to the x minus 2. You end up getting negative 1 to the 4th power, which is 1, and x minus 2 to the 4th power, which just stays at x minus 2 to the 4th power. After that, what I see that I have is that 4 plus 3 plus this 1, which is 8. So I have an even degree polynomial. That's exactly what I was looking for too. I wanted an even degree polynomial to kind of see, well, what happens to the n behaviors when n makes it an even degree polynomial. So let's go ahead and solve this out. I have a degree of 8, so it's an even degree polynomial with a negative leading coefficient. So like before, let's go ahead and just draw a picture, kind of graph it out. It's not really too hard, so let's go ahead and just knock it out. I have x-intercepts at -3, at 0, and at +2. And what happens here, since it's an even degree polynomial and it's the leading coefficient is negative, I'm going to start down and I'm going to end going down as well. So at x equals -3, I go through it kind of cubically. I go through it with a concavity change. So start from the bottom, I'm going to kind of cave in and cave back out. And then at 0, I go straight through it. And then at 2, I have the degree of 4, an even degree. That's very ugly, I'm not sure it's all crooked like that. But at x equals 2, the x-intercept there, I bounce off of it because it's raised to an even degree. So that's kind of what your graph is going to look like. But the important thing here is the end behavior. And I can see that my end behavior is as x goes to infinity, f of x goes to -infinity. And as x goes to -infinity, f of x also goes to -infinity. And that's it. That's it for the lesson, guys. Let me put this in full screen as well so you can see all the work. So take a picture, pause it, do whatever you need to do. But this is the work for number 13. Hopefully this was helpful, guys. I know Miss Winfield's students are watching this the day this we kind of get this out on November 29th. If y'all have any questions, I'm Mr. Aziz. I'll be in room 2234. Feel free to stop by if you need any clarification for anything on these problems. I know these can be a little difficult. I'll be here after school on 11/29 if you need any help with these problems. But anyway, this is the homework. The homework is to finish the rest of the homework packet. It's due whatever day your teacher tells you it's due on. That's the closing problem if you want to go ahead and give a shot at it. But this is it, guys. I'm not going to make this any longer than it needs to be. Hopefully this was helpful, and have a great day.